Hello dear students. So far in our discussions we have understood what is Debye shielding, what is plasma frequency and how we can derive expressions for both these parameters, and in terms of these two parameters we have been able to define the plasma criteria, which are essential conditions for calling an ionized gas as plasma. In today's class we will take up some numerical examples based on all these topics. So, the first question is based on the Debye shielding, which is based on the thought experiment that we did to establish the nature of Debye's potential, right. So, which is, let us say, a test charge plus Q is immersed in a plasma chamber, a plasma consisting of electrons and ions, right. Show that the effective charge inside the Debye sphere, because of all the shielding, cancels the test charge. This is the concept itself, right. So, where we have learnt that if you put a positive charge, all this electron cloud will be sufficient to nullify this positive charge, right. So, to do this, to prove that the total charge in the electron cloud will be minus Q, right. So, we can start from the expression for the density, which is E times N I minus N E. We know that the number of electrons is N naught e to the power of minus E phi by k T I, N E is N naught e to the power of minus plus E phi by k T E. Substituting both of these, the charge density rho of R can be written as E N naught e to the power of minus E phi by k T minus e to the power of plus E phi by k T. Expanding the exponential, we can write rho of R is equals to E N naught. This is similar to what we have done in the last lecture. E N naught into 1 minus E phi by k T I minus 1 minus E phi by k T E, which is equals to, we have a minus E square N naught E square N naught by k times 1 by T I plus 1 by T E. Using what we know for 1 by lambda d square, you can remember from the last class, we can rewrite this expression as rho of R is minus N naught E square by k times 1 by T I plus 1 by T E. So, we know that 1 by lambda d square is equal to N naught E square by epsilon naught k B times 1 by T I plus 1 by TE. Using this, what do we use it for? All of this. N0 kb for this part. Yeah, all of this actually can be written as N0 E square. So, epsilon naught is missing, right? These two things are one and the same. So, if we make a simple substitution, we will be able to write this equation as rho of r is equals to minus is still there, epsilon naught phi, yeah, there is a phi here, epsilon naught phi divided by lambda d square. Right. So, everything now you are able to follow. Rho of r is epsilon naught phi by lambda d square. Now, we know the charge density seems to be a function of the device potential and the device length and the constant, right. Now, we know that phi, the potential, the device potential is 1 by 4 pi epsilon naught to q by r e to the power of minus r by lambda d. We can use this and write the combined expression for the charge density is minus epsilon naught by lambda d square times 1 by 4 pi epsilon naught times q by r times e to the power of minus r by lambda d. When we know the charge density is charge per unit volume. When we know the charge density, we can find out the charge by integrating the charge density over the entire volume, right. So, total charge, the charge density, where is this charge density available? This is available within the device sphere. We can calculate the total charge by, let's say 0 to infinity rho of r 4 pi r square dr. Substituting what we know already is minus q by lambda d square integral 0 to infinity r exponential minus r by lambda d. We have the epsilon naught will get cancelled here itself, and 4 pi, this factor 4 pi will get cancelled with the 4 pi that appears here, and effectively what will remain is this. This is the total charge that is available within the device sphere. So, this is similar to what we know in mathematical physics. You must have studied. If I, let's say, make a substitution by r by lambda, calling it as x. So, dr by lambda d becomes dx. So, total charge within the device sphere is minus q integral x e to the power of minus x dx. dr is lambda d dx here, and if you substitute r is equals to x lambda, lambda d square will appear in the numerator, that will cancel this lambda d square. Since you have already used r in terms of x, it will be x e to the power of minus x. So, this integral is a pretty standard integral which is called as the gamma function. So, total charge inside the device sphere is minus q times gamma of 1. So, gamma of 1 is 1. So, the total charge is minus q, which means that for a positive charge, for a positive test charge of magnitude plus q that you kept out inside the plasma, the total effective charge that is trying to nullify this inside the Debye sphere is exactly opposite, right, minus q. Right. So, this is the proof for Debye shielding in a way, right. Now, let us say we take another example, example number 2. So, we can write the formula for device length by substituting all the known values of constants. We can write it as 69 times square root of T by n when the temperature is in Kelvin. Okay. So, we know that 1 electron volt is equal to 11,600 Kelvin. So, we use the notation or we use the unit of electron volt to describe temperatures in plasma, or lambda d can be written as 7430 times kT by n raised to the power of half when you are using energy as kT in electron volt, or the plasma parameter Nd can be written as 1.38 10 to the power of 6 T to the power of 3 by 2 divided by n to the power of half when T is in Kelvin. Do not think how I got this formula. We have already derived the formulas. You just have to substitute the known values of constants, you will get this, right. Using this, because it is very essential that we always remember plasma criteria. Using this, we can consider a variety of plasma that is available in the universe and calculate these parameters. For example, if you consider, what I'll do is I'll list the various types of plasmas. Let's say interstellar plasma. So, the number density of interstellar plasma is of the order of 10 to the power of 6. This number density is written in the units of per meter cube, that is number of particles per meter cube, and the temperature of plasma in the units of electron volts is of the order of 10 to the power of minus 1. Now, if you calculate the plasma frequency for this using the plasma frequency in hertz, which will be like 9 square root of n hertz. What is this? Is the frequency. It will be of the order of 10 to the power of 4 hertz, and the lambda d, the device length, would be approximately equal to 1, and the plasma parameter Nd would be equal to 4 10 to the power of 6. Lambda d has the units of meters and Nd has the units of per meter cube. Then another type of plasma you can find in solar corona, which has a typical number density of 10 to the power of 12, and the temperature is 100 electron volts. The plasma frequency will be of the order of 10 to the power of 7 hertz, and the device length is 10 to the power of minus 1 meters, and plasma parameter is 4 10 to the power of 9 per meter cube. And then you have chromosphere. The density is very high, 10 to the power of 18. the electron temperature is 1, 10 to the power of 10 will be the plasma frequency in hertz, and 7, 10 to the power of minus 6 meters is the device length, and it will be 1.4, 10 to the power of 3 per meter cube, the plasma parameter. Ionosphere is another region where plasma can be naturally found. The typical densities are of the order of 10 to the power of 12 per meter cube. The temperature is 10 to the power of minus 1, and plasma frequency becomes 10 to the power of 7 hertz. The device length is 10 to the power of minus 3, and device parameter, the plasma parameter, is 3 to the power of 4 per meter cube. And you have another man-made plasma, tokamak, which will have densities, very high densities, and at the same time very high temperatures. The plasma frequency will be of the order of 10 to the power of 11, and device length would be 7, 10 to the power of minus 5 meters, and 1.4, 10 to the power of 8 per meter cube, right. So, these are all you can calculate using the formula yourself and get the same values, right. But I am trying to make a point here. The point is, you see, the densest plasma is 10 to the power of 20 per meter cube, which is very, very dense. Its temperature is also very high, right. But you see, the device length is very, very small, whereas interstellar plasma is very weak. 10 to the power of 6 particles per meter cube is very, very weak actually. Temperature is also less, but device length is almost 1 meter, right, and the number of particles within the device sphere will be of this order. Now, the point is, it again reinforces the understanding of device shielding, what we have learnt in device shielding, that if the temperature is very, very large, the device length would increase, and if the concentration of charged particles is very, very small, or if the concentration is small, the device length would increase. If the concentration is high, the device length would decrease. That is why the plasma is so dense that it takes very small distance to screen out or to shield out the external electric fields or external charges, right. So, these things go hand in hand. We can take one more example to visualize how much density are we talking about, or what is the relevance of density. Let us say example number 3, calculate the density of ideal gas, let us say at 0 degree Celsius and 760 torr of pressure. Second part is calculate the density of ideal gas near vacuum at 10 to the power of minus 3 torr of pressure at 20 degree Celsius. This example can help you visualize how weak or how strong is this plasma in comparison to the average molecular densities that we have in the atmosphere, that or in the air that we breathe. Okay. What have we given? We have been given the temperature at 0 degree Celsius and at 20 degree Celsius, and we have also been given the pressure 760 torr. So, we know that the standard temperature and pressure under STP conditions, a mole of an ideal gas contains 1 mole of an ideal gas contains nearly 6.022 10 to the power of 23 molecules, right. which is called as the Avogadro number. And these many molecules occupy 22.4 liters of volume, right. So, we know that how many molecules are there and how much volume they would take up. What we have to find? We have to find what will be the density per unit volume, right. So, that can be found density or number of atoms or molecules per unit volume, let us say per meter cube, is equals to 6.022 10 to the power of 23 divided by 2.24 10 to the power of minus 2, which will be made a conversion of liters to meter cube, 2.66 10 to the power of 25 per meter cube. What is this number? This number tells you how many number of atoms or molecules are there within a unit volume at the surface at 0 degrees Celsius, right. If you put this to perspective with plasma, plasma is very weak. At least if you put this, at least there is 3 orders of magnitude, 5 orders of magnitude weaker than the air that we breathe, right. Although plasma has all these characteristics, but it is a very, very weak distribution, right. Now, the second part, this is the answer for the first part. For the second part, B, we know that PV is equal to nRT, where N is N by V, which is equals to P by RT. So, that means that if you remove the constant R, we can write N1 by N0. N1 can be something that you want to find out, and N0 is something that you know already, is P1 T0 by P0 T1, right. So, N1 can be taken as this one, 2.66 10 to the power of 25 per meter cube, and you've been given 2 temperatures, right, at 20 degrees Celsius. Then you can find out what is, sorry, N0 has to be this, N0 has to be 2.66 10 to the power of 25 per meter cube. You have to find the value of N1. So, N1 is N0 P1 T0 by P0 T1, which will be 2.66 10 to the power of 25 multiplied by 10 to the power of minus 3, 273 0 degrees Celsius by 760 in torr into 273 plus 20 at 20 degrees Celsius. So, the pressure is, 2 pressures are given, 10 to the power of minus 3 torr and 760. So, if you do this, the value that you will get is 3.30 10 to the power of 19 per meter cube, which will be N1. What is this N1? N1 is the number of molecules that will be present at this pressure and at this temperature. In order to get this, what you have used is, you have used a known value of temperature and pressure and the number density. We are calling it as N0, right. So, which means that since it is the atmosphere, it will have this many atoms even at such a low pressure. Near vacuum conditions also, there are this many molecules per unit volume. So, based on all these aspects, we will try to discuss some more numerical problems in the next lecture.